Well, hello everyone. This video is recorded for the Computer-Aided Verification Conference in 2022. And the title of our talk is Affine Loop Invariant Generation via Matrix Algebra. My name is Yuchen Ji. I'm now working as a postdoc in Shanghai Jiao Tong University, as well as OS Kernel Lab in Huawei Technologies Company. This work is joined with Professor Hongfei Fu in Shanghai Jiao Tong University and my colleague Bing Fang in OS Kernel Lab, and also with my postdoc mentor, Professor Haibo Chen. So, the topic of our talk is about loops, which are essential parts of programs. A while loop usually takes the following form. First, we have a program with a couple of program variables. And a while loop inside program should first have an initial condition, theta, which is usually a logical assertion on the program variables. Okay, and then we have a loop guard denoted by G, okay, which is another logical assertion. And we will check that if the initial condition satisfies the loop guard or not. If so, then the variables would enter the loop, and the values of them will be updated. And we call this process as transition relation. Inside the loop body, we might have some different branches. So we assume that inside loop body, we have possibly k different conditional branches, denoted by tau 1 up to tau k. As long as the program variable satisfies the loop guard, this iteration process will be repeated. But if at some time the renewed variables violate the loop guard, then the loop would stop. Okay, what we aim for from those loops are so-called invariants. So invariant is another logical assertion on the program variables. But it needs to satisfy two conditions to be an invariant. Okay, so those two conditions are called initiation and consecution. Okay? We call them as inductive conditions. The initiation is easy to understand. Basically, it says that the initial condition theta satisfies the invariant. So the invariant was satisfied at the very beginning. And the second condition is called consecution. So consecution means that if the invariant was satisfied by the variables before the loop iteration, then after the loop iteration, the invariants are still satisfied by the renewed variables. Okay, so more specifically, we have some known conditions which are loop guards, and the invariant before the loop iteration and the transition relation. Okay, they are all known to be hold, and then we should have that the invariant after the loop iteration also holds. Okay, and we assume that everything happens in the affine world in our work. Okay, the affine basically means a little bit more than linear. It's just a linear stuff plus a constant term. So an affine inequality phi is an inequality of the form of linear combinations of the program variables plus a constant d less than or equal to 0. Okay, and we assume that everything in our context is affine. So we aim for affine invariants of affine while loops. So the initial condition and the loop guard G and all transition relations and the invariants we want to find, they are either a single affine inequality or a finite conjunction of affine inequalities. And of course, we should be able to write them down in a mathematical form. So the most important thing is that the transition relation tau can be written as a relation, can be written as an affine relation between the variables after the iteration and the variables before the iteration. So the two variable sets are denoted by two vectors, and they are connected by the matrix multiplication by a matrix of numbers t, and plus a a constant vector. Okay, this T in this context is n by n square matrix. Okay, so we need a principle to decode the inductive conditions. And this principle was first established by a paper published also in CAV 19 years ago, okay, by Colin and others. So this paper used Farkas lemma to set up everything. The Farkas lemma is a theorem in the theory of an affine inequalities. It basically says that suppose we have k inequalities known to hold, represented by a11 times y1 up to a1 add up to a1n times yn plus b1 less than equal to 0. And we have such inequalities, we have k such inequalities. And we want to verify that another inequality, c1 times y1 add up to cn times yn plus d, is correct or not. We basically want to check that if this inequality is implied by the non-inequalities. And the Farkas lemma says that phi is implied by S if and only if phi is a non-negative linear combination of the inequalities in S. So the parameter, the coefficients must be non-negative because we are working with inequalities. Okay, and as long as we can solve out the solution for the parameters lambda r1 up to lambda k, then we know that the inequality phi is implied by S. Otherwise, it is not. Okay, so we can apply this to the inductive conditions. The most important thing is to apply this on the consecution condition. Okay, so we can write down the consecution condition in this table with the known conditions above the horizontal line. Here is the invariant phi before the loop iteration, and the loop guard and the transition relation. The transition relation would contain both variables before the iteration and after the iteration, and they together should be able to imply the invariant after the loop iteration. Okay, and we put non-negative parameters mu, psi, eta here. We mean that we multiply them on the corresponding row, and we add them together. We should be able to produce the inequality at the bottom. Okay, and by comparing the coefficients of x here above the horizontal line and below it, we get some constraint here written in this form. So the problem is this constraint is not linear, right? Because we have mu as an unknown parameter. C is the coefficients for the invariant. This is something we aim for, right? And psi is also unknown parameters. But T transpose and transpose are given matrices. So this has quadratic term, which is the first term. Then it cannot be directly solved by linear algebra or linear programming, right? So we need to develop a system of new methods to solve it. Well, the paper published in 2003, and they have another paper. They indeed impose some methods to solve this quadratic constraint, but their methods were not complete. And our contribution is to develop a systematic and complete solution to this problem. Okay, our contribution. So we have first result on using the eigenvalue and the eigenvectors for of the transition matrix. Okay. So the first theorem says that when we have a loop whose loop guard is tautological, then vector C is an eigenvector of the transpose of the transition matrix T transpose. So this is a pretty clean result. We omit the proof here because we want to show the power of this theorem by a concrete example. Example, Fibonacci numbers. It has initial condition x1 equals to x2 equals to 1. So this means that this sequence starts with term 1, 1. And the third term and all other terms are merely the sum of the previous two terms. So the transition relation is written in this way. x1, x2 prime equals to this matrix times x1, x2. Okay? So the renewed variables are just like one term later than the old variables. Okay, so x1 prime. During the loop iteration, we push x1 prime by one term backward. I should say forward. So x1 prime is equal to x2, and the x2 prime is the term after the two given terms. So x2 prime is x1 plus x2. Okay, so this is the recursive formula for the Fibonacci sequence. So from this relation, we solve out the two eigenvalues for this matrix, which are 1 plus minus square root 5 divided by 2. And we solved out two corresponding invariants here. The more important one is the second one. So it says that twice the x1 plus 1 minus square root 5 times x2 has two bounds, has a negative lower bound and a positive upper bound. Okay, so this holds for any two consecutive terms in the sequence, and this inequality basically means that the ratio of two consecutive terms in the Fibonacci sequence are very, very close to the golden ratio. Okay, so if the both bounds are 0, then it's just the golden ratio. Right, but we know that the golden ratio is never achieved in the Fibonacci sequence. It is just being approached by the back-to-back terms in the Fibonacci numbers, and this invariant indeed reflects this feature of the Fibonacci sequence. Okay? And this cannot be done by the traditional method, okay? Because they cannot deal with the irrational eigenvalues of a complicated transition matrix. Okay, and the next result is that for the loops with non-tautological loop guard. Okay, so in that case, we can also focus on the transition relation itself, and still use the eigenvalue method. Okay? But with the additional loop guard, actually we can make μ's to be values other than eigenvalues as well. Then we have some other new invariants given in the form of this formula. Okay, T transpose minus mu times identity matrix, and doing the inverse matrix and time the coefficients of the loop guard. Okay, coefficients from the loop guard. Okay, so this is a directly computable formula for C. Okay. And psi is a free non-negative parameter, can be taken by any non-negative values. Okay, but so in this way, we actually see that C is a linear subspace. Okay? It's not just one vector. Okay, it's a linear space as well as the eigenspace. Right? The eigenvector are also linear space stuff. So we indeed have some freedoms in the invariants, but we can fix those freedoms to get the most important invariants. So we have an example. Also, two variables initial condition are that those two variables are both 1, and we have a loop guard as a finite conjunction of two affine inequalities, with x1 has an upper bound, x2 has a lower bound. And during loop iteration, we increase the value of x1 by 1, decrease the value of x2 by 1 every time. Okay, and we want to see what we can do, what we can get from our eigenvalue method and matrix inverse formula. So we have results. The first, if we take mu to be the eigenvalue, then we apply the eigenvalue method. We have three independent three independent invariants. So the first two, they show that the sum of x1 and x2 is a constant. It's zero. It's 2, right? Because x1 and x2 has the same initial value 1, and the value of one variable increases by 1 every time. The value of the other decreases by 1 every time. So the sum of those two numbers is indeed 2, right? So the eigenvalue method gives us a pretty strong invariant. And the second one is that x1 is always larger than or equal to x2. That's also something useful information. And for the values other than eigenvalues, right? We actually have infinitely many choices for them to get infinitely many possibly independent invariants, right? But we don't have to use all of them. We usually use the most boundary ones because they usually give us the sharpest invariant. But first, we take one boundary value 0 because we know mu got to be non-negative, right? And this choice perfectly reflects the loop guard. Okay, we recover the loop guard as an invariant, which is also good. And we choose another kind of boundary value. We get that x1 larger than 1 and x2 less than 1. Larger than 1 and x2 less than 1. Right. So this also reflects the feature of the variables during the loop iteration. Okay. And we want to see if how powerful those methods are for more benchmarks, right? Because we just tested 2 examples. So we implemented our methods, the both eigenvalue method and the matrix inverse method in Sage. And we run a dozen of examples on our program. And the results are shown in this table. Okay. So we have like more than 10 benchmarks. We have the choices of value mu. And we have the corresponding variants. And we compare our results with the existing benchmark, with existing tools. The Stanford invariant generator, STIN, and invariant generator, and again, we compare our results with their results and benchmarks. We see that for almost all benchmarks, our invariants recover or outnumber the results by the previous ones. Okay, especially for the examples with complicated transition matrices. We know that we usually have complicated eigenvalues for those matrices, right? On those examples, basically, STIN and again cannot produce any useful invariants, but we can get a lot of invariants with irrational coefficients, okay, which is only possible from our method. So our work is indeed a big step forward for the linear and affine invariant generation for the loops. Okay, so that's all for my talk, and thanks to everyone for listening.